Okay guys, so in this video, we're going to be checking out an organic synthesis question, okay? Unfortunately guys, I can't actually show the question paper on the screen because of AQA's copyright, but I've rewritten the question slightly and I've drawn out the reaction scheme so you can see exactly what's going on. But if you want to see the paper yourself, it'll be linked down below in the description. It's paper 2, June 2020. I'm not sure if I mentioned this, but this is the AQA specification. So let's jump into the question and see what's going on here. So polystyrene can be made from benzene in the series of steps shown below. And we're given a reaction scheme here, and we have to use this to problem solve and work out what's going on. So what does question 6.1 say? What reaction is occurring in step 1? And we also need to identify the reagent as well as the condition. So a very typical organic synthesis question here. Now, I'm going to actually outline my thought process behind any organic synthesis question. And it's going to be a combination of two things, all right? Firstly, memory. Okay, where am I going with this? All right, I'm actually going to put something else here as well. Understanding. Okay, now for this organic synthesis topic, the reason I put memory here as our primary thing that we need to focus on is you need to know every single reaction, mechanism, reagent, and condition for the entire AQA specification. Okay, so every single functional group, how they interlink and map with one another, and how you ultimately go from one thing all the way to another, okay? If you can memorize this map with a combination of flashcards and blurting that stuff on the page in mind maps and stuff like that, you'll be completely fine as a head start. The reason I put understanding right here is because if you understand how the reactions work, it allows you to get those A stars, right? But you can definitely get an A just with memory. Okay, so just keep that in mind. Memory is really good. Memory is fundamental. You want to focus on that first. But if you can actually understand why things are happening, intermolecular forces, what is going on here, it's going to allow you to connect things in your mind. And that's where chemistry really starts to click. When you understand the fundamentals and you understand what's going on, that's when you can really border into the high A's, A stars, right? Number 2. What's number 2? It's going to be process of elimination. So let's write that out. Process of elimination. Okay, not the mechanism elimination, process of elimination. You want to think to yourself, what is my reactant and what is my product? Okay, what do I mean by that? Primarily, I'm thinking of functional groups. So if we look at this first one, this step 1, which feeds directly into question 6.1, what is the functional group here? Hopefully it's an easy one. Benzene, right? So benzene. Let me write this out. This would be my thought process. I'm not going to write all this on the page in my exam, but this would be my thought process. What is the functional group of our reactant? Boom, on the page. What is our functional group present in our product? What is this? You know? Whoop, ketone, right? That's our functional group. So ketone. Okay. So process of elimination then, we've got our functional groups and we have to think, okay, how do we go from benzene to a ketone? Now I'm going to take this one step further. Benzene comes under the aromatic topic in AQA A-level chemistry. So I'm going to write this out here. Bear with me guys, bear with me. Aromatics, right? What type of mechanism or reactions occurs in the aromatics topic? You should know this. If you don't know it, you should memorize it. Okay, the type of mechanism that is included in this topic is electrophilic. All right, what is it? Electrophilic what? Is it addition, substitution? Substitution. Okay, electrophilic substitution. Now, electrophilic addition would have been alkenes, but for this, electrophilic substitution. This further breaks down into two separate categories that we can think about. We can think about nitration. Okay, that's one of the types of electrophilic substitution that you need to know. The other one is Friedel, I hope I'm spelling this right, I always mess up the spelling. Friedel-Crafts acylation. Okay, sometimes it's shortened to just acylation, but I like to chuck in the whole term here for you guys. Friedel-Crafts acylation. So again, going back to my point 2, process of elimination. We've got an aromatic substance here reacting. We've got a benzene. Okay, so electrophilic substitution. Is it going to be nitration or is it going to be Friedel-Crafts acylation? Is there a nitrogen present in our product? No, there is not. There's no nitrate group. So it has to be Friedel-Crafts acylation. So process of elimination has reached us with what sort of reaction is taking place. So that is our first mark done. What reaction is occurring? Friedel-Crafts acylation. One juicy mark done with the process of elimination, combined with memorizing the step-by-step breakdown of what is involved in the specification. Okay, so we did that. Now, as I mentioned, if you look at the mark scheme of this paper, it only says acylation. And that's because I suppose AQA was feeling friendly and that's what they accept. But please just try and remember the full terminology, because AQA is inconsistent as hell when it comes onto their mark schemes. And sometimes they put stuff, sometimes they don't. So I would say, personally, stick with the full term of Friedel-Crafts acylation, but feel free to just remember acylation if it's easier for you. Okay, so that's the reaction done. Next up, what is the reagent? Okay, the reagent for these Friedel-Crafts acylation is always going to be an acyl chloride. Okay, so even though that we know the functional group of the reagent is going to be an acyl chloride, we can't just chuck acyl chloride on the page. Anytime they ask for and I'm going to highlight it, reagent, you have to name the specific chemical. So if we look at our product here, again, using process of elimination, we can see the name of this ketone chain here is going to have 2 carbons in it, right? So we know that a reagent has to have 2 carbons. So if we think to our naming system, 2 carbons is ethan, and then the remainder of the molecule name for an acyl chloride is going to be oil chloride. So therefore, it's going to be ethan for 2 carbons, oil chloride. Okay, so we've got our reagent here. Now, something I saw in the mark scheme, and I'm just not a fan, guys. I'm not a fan of this, the way that AQA set this out. So I would have personally done the reagent as ethanol chloride in the presence of aluminium chloride catalyst. Okay, that is you have to have both as the reagents, but they've actually included the catalyst as the condition, which I suppose is okay. I'm just not a fan, but that's essentially what they want to see. For both nitration and Friedel-Crafts acylation, you're going to need a catalyst. Okay, in this instance, the catalyst is aluminium chloride. So let me put aluminium chloride down here. That's our condition. So let's make this clear. So we've got our reagent and condition. Now, this aluminium chloride has to be anhydrous, okay, or in the absence of water. Again, they don't really require that. They put it in the extra column of extra information to allow it, but you don't need it. So if I was writing this out myself, my own flashcard, I would put acyl chloride as a reagent in the presence of an anhydrous aluminium chloride catalyst. All right, that would be my reagent. Condition is heat under reflux. They don't mention it whatsoever in the mark scheme, which I find kind of strange, but there we go. So maybe in this new format, they want to see the condition as the catalyst, which makes no sense to me, and I keep repeating myself. So I'm gonna move on before I just rage out. So there we are, 3 marks in the bag. There we go, 3 nice marks. All right. Again, memorizing. I memorized the reagents. I memorized the conditions. I memorized the catalyst. I memorized what the mechanism was called. I memorized what the reactions were underneath the umbrella of the mechanism, okay? You need to be doing all of these things to just guarantee the marks. And if I saw this on my exam, right, it would take me 30 seconds to get all 3 of these marks, maybe less, just because you've put in those hours, those days of revision beforehand to get it on the page. And that's what you really want to do in chemistry to get those A's, A stars. You want to put the work in so that you can be time efficient as possible in the actual paper, right? So enough rambling, enough ranting. Let's move on to 6.2. I don't think I've missed anything here. No, so we're good to go. Right, so question 6.2 then. What is the name of the mechanism in step 2? And we also need to identify the inorganic reagent and name the product. All right, so they switched things up on us here. Very similar format of a question, but instead of being reaction, reagent, condition, they switched it out to be mechanism, inorganic reagent, and product. All right, so it's a few different things going on here. Again, I'm going to use the process of elimination and memory. Combine those two things, organic synthesis, you should get, like this entire question 6 is 10 marks. You should get 10 out of 10 marks every time. Okay, now, as I said, I'm running out of space, so I'm quickly going to copy and paste this over to a new sheet and start again. All right, so I've moved stuff around, created some more space for us. I'm going to rub this out as well. Reaction, that's no longer our reactant and no longer our product. We're now interested in step 2. So we're going to have this as our reactant. Let's also rub this out. Boop. And this is going to be our product. Okay, exact same process of elimination. What is our reactant functional group and what is our product functional group? So I'm going to pause here for a second and let you think. Hopefully you guys are screaming at me right now. So this right here, what is this? We already named it in question 6.1. It's a ketone, all right? And what are we transitioning to in this step? We are transitioning from a ketone, more specifically a phenyl ketone, into a secondary alcohol, okay? Secondary because it's got 2 carbon chains attached to it, so we know that it's going to be secondary. So I don't really think that's important here because we're not dealing with oxidation, but nevertheless, I'm going to chuck it on the page because I've memorized it and it could help me potentially in a different question that comes up. So we're going from a ketone to an alcohol, okay? All right. I'm laughing here because I keep repeating myself, but process of elimination, okay? Ketone comes under the ketone and aldehydes topic in the specification. If you know the specification like the back of your hand, you should know the only mechanism involved in this is going to be what? Come on, guys. Nucleophilic addition. Okay? That's literally the only thing we can pick. You don't even really need to know what's going on. You can hopefully get 1 mark there as nucleophilic addition. Now, inorganic reagent. So this inorganic reagent is going to be this guy right here. Sodium tetrahydroborate. Okay, a real mouthful right there. Now, again, you don't need to know the full name. They will never ask you to name this. It's always just this. So I recommend NaBH4. Get that on the page. 1 mark out the way, right? This is the inorganic reagent. This is going to break up, right? And it's going to provide a hydride ion, which is something you don't normally see, a negative hydrogen ion, okay? You're never going to normally see this, but this is actually attracted to this guy right here, okay? There's a dipole existing here between the delta positive carbon, delta negative oxygen, and this is going to be attacked onto there as a nucleophile, right? Alternatively, you can have lithium aluminium hydride. So it's sort of like this molecule right here, but it's going to be lithium aluminium H4 again. Okay, lithium aluminium hydride. So that's our 2 options out the way for what the inorganic reagent is going to be. What is the product? All right, this is some interesting stuff here. I always enjoyed nomenclature because once you get a hang of it, it's easy marks, right? So we started, again, going back to process of elimination, we started with a benzene right here, okay, C6H6. Once this has reacted and it's now got a side group on this, an R group instead of a hydrogen, so normally like we've got a hydrogen here, right? This hydrogen is no longer there. It's been replaced with some sort of organic molecule, whatever we're dealing with. It becomes C6H5. Now, do you remember what the name of this functional group is? It is a phenyl group, right? C6H5. Now, when benzene is in a molecule, for example, let's say we just had like a cheeky methyl group on here, right? This is going to be methyl, and then the suffix of benzene is the priority group. So benzene is the priority group in this molecule, therefore it's the suffix. That's how nomenclature works, okay? You're going to have the suffix, the end portion of the name. You're going to have the prefix, the beginning portion of the name, and then what the hell is in the middle, right? And the way that priority works in naming molecules in organic chemistry is the suffix is always going to have the highest priority. It's the big boss of the molecule, right? That's the way you have to think of it. So when we transition from a benzene, which has the highest priority, to a phenyl group, this now has the lowest priority, okay? That's the way I like to think of it. I like to think of it because they don't really teach this, right? I was never taught it. I've never found it in the textbook. I'm not a chemistry teacher. I'm just a dude that got a good grade. Now, when I think about a phenyl group, I think of it as an alkene more so than a benzene or an aromatic compound. So I think of it, once it's broken down into a phenyl, more like this, right? An alkene. That's how I kind of think of it. Now, this is probably incorrect, and feel free to just completely ignore what I'm saying. But the reason that I'm saying this is because when we're naming organic molecules, an alkene is always going to have a lower priority than an alcohol, right? So if I'm looking at this and I'm saying, okay, what are our functional groups present? We've got a primary alcohol, a secondary alcohol right here, ethanol, right? Ethan-1-ol. And we've got a phenyl group, and we have to name this molecule. This is a greater priority, therefore the alcohol is going to be the suffix, right? Hopefully you're with me. So if we draw the suffix out, ethan-1-ol, right? Our suffix is done. All we need to do is chuck on the prefix, which we know can only be the phenyl. Okay, and if we look at our alcohol group here, the highest priority carbon in our alcohol carbon chain has to be bonded to the highest priority functional group, which happens to be this hydroxyl here, this alcohol. So we know then that this is going to be carbon 1 and this is going to be carbon 2. That's just how it works. If you don't understand, you're going to have to practice some more basic questions. So then, when we name this, we need to name the position on the carbon chain that this phenyl functional group is bonded to. So it's going to be 1 phenyl, ethan, 1-ol. Okay, so let's do that. 1 phenyl, ethan, 1-ol. Okay, that was real long-winded, but hopefully it gave you some insight into naming molecules. Feel free to completely ignore this alkene thing. It's just like the way I like to think of the benzene molecule once it's become a phenyl. Right. Woo! Just over halfway. Right, let's carry on. 6.3. So the organic product of step 2 is then reacted with concentrated sulfuric acid in step 3. Draw the mechanism for step 3. So we established that in step 2, we had a secondary alcohol, right? So secondary alcohol. And we are producing this molecule here. What is this functional group right here? You should know straight away, hopefully, by the double bond, alkene, right? Alkene, done. So again, memory, process of elimination, repetition just gets you there, to be honest. So how do we go from a secondary alcohol, or any alcohol really, to an alkene? What mechanism is involved? So the only mechanism to choose from really under the alcohol topic to transition into an alcohol, an alkene, would be elimination. So even though they don't ask you to name it, I'm just going to put it here for you guys so you know it. Elimination. Okay, that's our mechanism. More specifically, it's referred to as acid catalyzed elimination. Okay. The acid is a catalyst here. So I'm sort of repeating myself here. But the reason being is that if we draw it out, let's just draw out the mechanism for you guys so you know what's going on here. Let's start with, so we're going from step 3. Let's draw this out. So we're going to have our phenyl group. And we're going to have our C. Oh, this whole time, guys, I missed off the H. Whoops. Just ignore that. Pretend that never happened. And then we're going to have our OH, and then we're going to have our H. So when I do mechanisms, I like drawing most of the major bonds just so I can, wrap my brain around what's going on. So what's going to happen here is we have an oxygen, right? Actually, let me bring this down a little bit because I'm going to run out of space. Let's bring this down here. So what's going to happen here is we're going to have a lone pair on the oxygen, right? Oxygen, group 6. Hopefully, if you guys have practiced this enough, you should see an alcohol group or an oxygen. Even up here, you should be like, oi, lone pair, what's going on? This is going to react with a hydrogen ion, all right? And this hydrogen ion is from this guy, the H2SO4, all right? Then after the reaction is complete, goes off in solution, reforms sulfuric acid, hence why it's a catalyst. Now this oxygen's feeling mighty lonely. It's only got one hydrogen, but it wants to react with this one as well. Oi, come to me. So, and the reason being, like in all these reactions, there's a dipole present, okay? Region of electron density is going to attract this hydrogen. This hydrogen is not only delta positive, it's actually full on a cation, right? It's a full on positive ion. So it's extra juicy, extra attractive to this oxygen. So it's going to suck it onto itself, right? So what's going to happen here is this oxygen is actually going to have a bad time and we're going to form an intermediate. So let's draw this intermediate out. Oh, it's a bit long, isn't it? Oh, C, CH3 again, H. We're going to have our O here. So it's actually going to be positive. Got 3 bonds here. It's not a happy boy. So what's going to happen is, again, dipoles. There's dipoles everywhere. Remember I said, when you understand the fundamentals of chemistry, it's going to allow you to just fly through these questions, right? So this is delta positive and this is delta negative, another dipole that exists in this molecule. This covalent bond here has 2 electrons within it, right? Shared pair of electrons. This oxygen is now positive because this, when it donated its lone pair to this hydrogen, this positive hydrogen ion, it's a dative covalent bond. It's lost both of these electrons. It's not a happy boy. So what's going to happen is this pair in this covalent bond right here is going to be kicked back off onto this oxygen, and this carbon is going to lose the electron within this covalent bond that belonged to him. This carbon has lost its electron to this oxygen, right? So that's our first intermediate. Now this mechanism actually involves 2 intermediates. We got to do another one here. So what happens next then is, I'm going to draw this out again, right? So we're going to have our phenol, we're going to have our carbon, we're going to have our CH3, we're going to have our H, and my puppy is scratching at the door. 1 second. Okay, the puppy is safe. We're all good. Crisis averted. So where was I? Let's continue. So we've got this additional intermediate here, right? This is a carbocation. As I mentioned, one of these electrons within this covalent bond belongs to this carbon, all right? It's lost it. It's just lost it. It's not a happy guy. So it is now a carbocation and it has to regain something onto itself, right? So where is the electron that it's lost going to come from? It's going to come from this methyl group here, okay? So I'm actually going to split this methyl up into showing all of the hydrogen bonds so you can see exactly what's going on. So I'm going to have a hydrogen here, hydrogen here, hydrogen here, okay? Now, one of these hydrogens, as I mentioned, is going to break off. The covalent bond is going to break and it's going to form a double bond right here because we are ultimately forming our alkene functional group, okay? And that's what's going to happen. Let's make this guy a bit longer. Whoop. And then what happens, as I mentioned earlier, this is an acid catalyzed elimination reaction. So this hydrogen, for example, is going to fly off in solution. Whee! Okay, all the way up here, H+, right? It's in solution, and it's going to react with the HSO4 minus that was from our sulfuric acid, right? And it's going to reform the concentrated sulfuric acid, H2SO4. Happy days, we're going to get our catalyst reforming. Okay, speeds up our reaction, lowers activation energy, all that good stuff. You know, the catalyst definition you need to know. So yeah, that's pretty much what happens. So that's our mechanism here. It's a pretty awkward one because there's 2 intermediates. We have our oxygen cation forming and we have our carbocation forming. Okay, now I've broken this up in the intermediate up into 2 stages, right? 2 separate reactions occurring. AQA actually wants to see this combined into one mechanism. I just broke it up so you could see exactly what was going on. But in reality, what you want to do, and also in case I haven't mentioned it, you don't need to show these partial charges, right? Whoops, didn't mean to erase that. You don't need to show the delta positive and delta negative. You just need to show the curly arrows, the lone pairs, and the charges, okay? So then, if I was doing this as the mark scheme wants to see it, and in my actual exam, I would have done this methyl group right here straight away in the second intermediate. Sorry, the second step of the mechanism. So I would have done one of these hydrogens. It doesn't really matter which one. I'm going to do this one this time. Boop, onto there, forming the double bond right here. And then this goes off in solution as H2O, right? So that's what I would have done there. Now, some of you may be looking at the mark scheme yourself, and you can see in the top part of the mark scheme where they have the mechanism, the first one, that they're reacting the alcohol functional group, the hydroxyl, with the full H2SO4 molecule, and then the HO bond is breaking off onto the O. So like this. So you'd have, let's draw this again. So we've got our OH, right? You have your lone pair on the O, and then we have our HO bond of the SO4, right? And then you have the remainder of the molecule. So your double bonds, I'm not going to draw the whole thing, so I have no space, but you get what I mean. And then this goes onto here, this breaks off onto here. Now, you can do it this way, and I think this is easier because you can just skip a whole stage and you don't get the opportunity to mess up at all. But you can do it like this if you want. It's just you skipped a stage, and this is the H+, okay? This is the H+ in this portion from the H2SO4. Okay, so I hope that helped you guys with the mechanism side of the question. Let's move on. Finally, 6.4, draw the repeating unit of polystyrene. Okay, so gotten a bit messy up here, but hopefully I can do it in the same stage. So we've got this right here. This is our alkene that we formed through the acid catalyzed elimination reaction, right? What we want to do is we want to form polystyrene. Now, polystyrene, given it away here, is a polymer, polystyrene. Okay, polystyrene, repeating unit. What does this mean? This means monomer. So the building blocks of the polymer, right? So you have to think to yourself, polystyrene, okay? We're dealing with an alkene. If we're forming a polymer from an alkene, we know that the double bond has to break, right? Let's get a nice juicy red for a cross. The double bond has to break, and if a double bond is broken, in order to form a polymer, we have an addition reaction occurring, okay? Doesn't really mention that anywhere here. I'm just giving you some nice theory. So the way I like to do this is I like to draw out my alkene, right? So we're going to have our C as our double bond. The reason I draw it like this is because I'm so used to doing EZ isomers and teaching people how to do it. Whoops, that bond's a bit off, isn't it? So the reason I draw it like this is just because I'm used to EZ isomers, right? Where we have it sort of in this structure. So we're going to have a H here, a H here, we're going to have a H here, and then we're going to have our phenol group here. I'm going to draw it real tiny because I've run out of space, right? This is our phenol group. Now, what's going to happen in an addition reaction is this guy is gone, right? And then we're going to get a bond either side of this carbon. Because these carbons are group 4 and they've lost their central double bond here, they need a trailing bond either side to make up the monomer, right? So I'm going to redraw this for you in the format that they like to see it in. The reason I drew it like this, again, as I mentioned, is EZ isomers. So C, this double bond is now a single, it's a saturated carbon. And then we're going to have our H's above and below, as well as our phenol group, right? So H, and then I'll draw this small again because I've completely run out of space. And then trailing bonds, super important. Trailing bonds just signifies that this can literally go on forever, right? It's polystyrene, it's a polymer. There's no limit to the amount of monomers that can make this up. Now, I like to chuck in the square brackets. I really do. Because it signifies to me, if I was seeing this notation, especially at uni and things like that, it's going to signify to me that this is a building block or a monomer or a repeating unit of a polymer. And I'd also chuck a lowercase n to signify that this can essentially happen an unlimited number of times. But surprise, surprise, AQA in the mark scheme says ignore brackets and any use of lowercase n. So I'm honestly just losing my mind at this point of AQA, but here we are. all you need to show, so I'll rub it out to know, so you know what you need to show, boom, boom, boom. That's all you need to show, okay? Is you need to show the alkene with the double bond broken, so it's no longer an alkene, it's an alkane. And we're going to no longer show the brackets, we're going to show the trailing bonds to signify that. You do need to show the trailing bonds, okay? Now, if you don't want to draw out the phenol group and you're feeling extra whatever, draw out C6H5, okay? That's the alternative formula that they accept instead of the, I like drawing these out. These are pretty cool. Gives some spice to the structure. Yeah, so that's the end. Finally, 10 marks, done. So I haven't gone into too much detail where the marks came from, but hopefully it's pretty self-explanatory. If we go back to question 6.2, we had the name of the mechanism. That would be the first mark. What is the inorganic reagent? This guy right here. And name the product, this guy right here. So that's 3 marks right there. And then within this question here, we're going to have drawing the mechanism. So you're going to get the first mark is going to be for this curly arrow right here from the lone pair on the oxygen onto the H+ ion, or alternatively, if you want to draw out the entire sulfuric acid molecule, but you do have to show this second arrow going, breaking the covalent bond between the hydrogen and the oxygen. The second mark here is going to be for this guy, this curly arrow, from the lone pair, sorry, not the lone pair, the covalent pair onto the oxygen. Also, you have to show that it's positive since it's gained this hydrogen onto itself and it's formed a dative covalent bond. It doesn't really like that. And the third and final mark is from this hydrogen bonded to the methyl group is going to break this covalent bond here and form the double bond within the alkene. So that's our 3 marks there. And then this one is just 1 mark for the final structure. You can't have any deviations from this outside of this instead of the structure of the phenol group. Okay, hopefully you guys found that helpful. I put an absolute ton of time into this and I probably rambled way too much. One thing, because there is no examiner's report for the 2020 exams because of good old, I'm not going to mention it, but you know what happened in 2020. Use this, okay? Use a combination of memorizing it with flashcards. Use whatever works for you. I like a combination of flashcards and mind map. So just chucking absolutely everything on the page, condensing my notes down further and further and further, and understanding the fundamentals that you look at it in AS and you think this is boring, this is not important, but it really is, okay? Bonds, intermolecular forces, stuff like this is really important. And then process of elimination. So looking, what are the reactants? What are the products? And just literally chipping away at it piece by piece, okay? That would be my sole recommendation to anyone that struggles with these sort of questions. Go ahead and like the video if you found it helpful, and if you want more content like this, share it with anyone that's really struggling with chemistry, comment any questions down below, and subscribe to help the channel grow. Best of luck with your revision, guys, and upcoming exams. Until next time, peace.